days. Yeah. So, what we were talking about last time, and I forget exactly how far we got into this. I think I just posted at the very end. But the idea, we've got edges of a cube, like you can maybe imagine it being projected on the screen, getting larger at a rate of 2 centimeters per second. So I think we talked about half of this. I'm going to kind of go over it quickly. We want to know how fast the volume's changing when the length of each edge is 50 centimeters. So then the idea with related rates is, if you have an idea of, let's see if I can fix the lights a little bit. There we go. If you have an idea of how the underlying quantities in a problem are related to one another, like in this one we've got edge lengths and volumes of cubes. So, oh, I know a geometry relationship for that. Volume of a cube is whatever the side length is or edge length is to the third power, cubed. So if you know how those underlying quantities are related, then if one of them changes, it's obviously going to change the other somehow or another due to that relationship. But the rate of change is related to derivatives, not just, it's not always changes at the same rate, like when one increases by 2, the other increases by 2 somethings. They're not even the same sorts of units. And in this case, we have the overall relationship. Oh, let me get my writing thing started. The overall relationship is here we go, that the volume of a cube is given by this, I'll just call it S for side length instead of E for edge length. Side length cubed, so it's a cubic equation. When I change the side length a little bit, the volume's going to change a little bit, but I'm not really interested in how the volume changes per centimeter change in side length or something like that. What I'm interested in is if the edges are getting longer at this rate of time, like a time rate here, centimeters per second, like a speed, I want to know what speed the volume is changing at. So the idea is I can think of volume as a function of time, because if the side lengths are changing at a certain rate, and we could actually write out the side lengths, write out some formula for side length that has a rate of change of a constant 2 centimeters per second, but we don't actually need to do that. You can think of this with function notation if this is helpful, because what we're trying to do, this 2 centimeters per second, this is a value of s prime of t, or if you like the slope style notation, ds dt. And our goal is to find how fast the volume is changing, which volume changing, that's a derivative of volume. This is how fast, meaning like with respect to time. So I'm trying to find v prime of t. That's our goal for this. Find v prime of t, or if you like the other notation, dv dt. And notice t isn't involved in this question because time doesn't help you calculate the volume of a cube in general. Just in this case it could, because you know how much time has passed would lead you to know something about how long the sides are. Now in actuality we don't. We don't know at what point in time the volume was 0 or 17 or anything else. We don't have a total accumulation knowledge. So instead of trying to figure out how long the sides are at any point in time and thus how big the volume is, we can just say, okay, I know enough from this. I know how the volume and the side lengths are related. So if I know how one changes, then I'll be able to figure out how the other changes by taking derivatives with respect to t. So I'm going to write this. I'm going to take the derivative of both sides of this equation. So just kind of thinking like an algebra. Do the same thing to both sides of the equation and you're good. So as long as it's nothing like division by 0, then this shouldn't cause any problems. I want to take the derivative of s of t to the third power with respect to t, and I want to take the derivative of v of t. Well, I don't have to do this. I'm just going to write the symbol v prime of t. The derivative of v of t with respect to t is called v prime of t. The derivative of this function cubed, where it's a function of t is the independent variable in it. The derivative with respect to t, so this is like f of x, and I'm trying to find the derivative of that with respect to x if you like other variables. The derivative of this one would be, let's see, well, 3 times whatever s of t is to the second power times, chain rule, the derivative of s of t, which is s prime of t. So here's a relationship. So relationship number 1 up here relates volume and side length, and that's it. Relationship number 2 here that we created by taking the derivative of that first relationship relates 3 things, notice in it, and it depends on the function exactly how many pieces are going to be involved, because it's all to do with chain rule in this case. I have the rate of change of the volume, the rate of change of the side length of the cubes, or the edge length of the cube, and it also happens to involve what the side length actually is. So the rate of change of the side length as well as the side length itself, a value of that. Well, this is a formula for it, so all values of it for any value of t. But what we're looking for is the edges of a cube get longer at a rate of 2 centimeters per second. That's a rate of change of s. So this is 2. 2 is a value of s prime of t. I don't know what t we're talking about, but that doesn't actually matter. All I need to know is, let's see, it says how fast is the volume changing when the length of each edge is 50 centimeters. So I don't need to know the point in time, I just need to know the side length at that point in time. So that's great. When the edge length is 50 centimeters, that means s of t is 50. And again, this is centimeters, this is centimeters per second. So this right-hand side is all numbers. We have numbers to substitute in. We get 3 times 50 squared times 2 equals this. And the units on it you can see would be centimeters times centimeters per second. Let's see, wait. Oh, centimeters. Sorry, this is squared in here. This is the part that's 50. So centimeters squared by the time I'm done squaring this. And then times centimeters per second gives me cubic centimeters per second as my units. And whatever the numbers are, 3 times 50 squared times 2. Would be the number corresponding to the rate of change of the volume of the cube at this particular point in time. And again, we don't have a point in time like at time 7. We just have the time when the side length is 50 centimeters. So in any case, we started with a relationship between 2 underlying quantities, volume and edge length, and we figured out by taking derivatives how changing one will change the other. And not dVds, not the rate of change of volume with respect to the side length, but the rate of change of volume with respect to time. We get to imagine there's this time variable in there. We can imagine that we know volume as a function of time and side length as a function of time, but take their derivatives anyway without knowing any more details, and that's enough information because of the way that this is all posed. I don't have to know points in time to be able to substitute into a time-based expression. I just have values for the dependent variables of those. All right, so on to a new question, maybe. There we go. So this is what we just did. All right, so the answer to all of that comes out to be 15,000 cubic centimeters per second. But that's only valid when the edge length is 50. If the edge length was something else, you can see, this would give us a different result. So the volume isn't always increasing at that rate. It's increasing at that rate specifically in the moment when the edge length is 50 centimeters. So, different question, same sort of idea. We've got, instead of a cube, we've got a sphere, a spherical balloon, and it's untied. It's letting out helium at 150 cubic inches per minute. And I want to know how fast the radius is changing when the volume is 500 cubic inches. So sounds like some of the same sort of information, slightly messier underlying relationship this time. A little harder to find the volume of a sphere than of a cube, but if you can see, we've got some of the same general things to think about. If we can come up with a relationship for the underlying quantities here, I can figure out how the radius changes relative to the volume at specific points in time. So in terms of this, since it is not familiar, and by the way, for your test, which is not 2 days from now Wednesday, but next week Wednesday, um, anything like random geometry formulas other than rectangles sorts of things, you will have a formula given. So volume of a sphere, though, is 4/3 pi times the radius cubed. So here's our underlying quantities equation that's going to be important here. So take a minute, see if you can figure out what given information we actually have, values of what sorts of expressions. That 150 cubic inches per minute and the 500 cubic inches, what are those? What are we trying to find? Like variable-wise, what is the thing, the expression or the rate or the length that we're trying to determine? And see if you can get started on that. This one's a little messier than the last one. All right, so we have a relationship between the volume of a sphere, and we'll just pretend that this balloon remains a sphere as the air comes out of it, so it's a fairly solid but small type plasticky thing. So in any case, we've got a spherical balloon, radius given by 4/3 pi times whatever, 4/3 pi times the radius to the third power. This 150 cubic inches per minute, that's a rate of some sort, I can tell by the units. It's a rate of change of what? Volume, right. So inches cubed or cubic inches per minute, this is a volume changing over time. So this is a rate of change of volume. Now, one note here, if I'm going to say that this is dV dt, is this correct? No, it's missing something. Yeah, it's small but important. negative. The rate of change of the volume with respect to time, think about as time goes on, what's happening to the volume? It's not getting bigger, it's getting smaller, right? The balloon is letting go of the gases inside, so it's shrinking. So if you happen to leave this out, your answer would also have a missing negative sign, and you might not even notice it. You might still interpret it correctly, but just technically speaking, this is our volume shrinking. So I want to talk about my volume decreasing at a rate of 150 cubic inches per minute. So units on this are cubic inches per minute, but just the value is negative 150. Let's see, how fast is the radius changing when the balloon has a volume of 500 cubic inches? All right, so we're talking about a moment in time when the volume is 500. We're supposed to be finding how fast is the radius changing. So how fast the radius changing, if I'm looking for a symbol to describe how fast the radius changes, what would I maybe write for that? Yeah, dr dt or r prime of t, whatever notation you like. This is the thing we're trying to find. And based on the problem, it should be shrinking, so I'd expect dr dt to come out negative. If you weren't thinking about shrinking versus growing and left out the negative before, it would just come out without the negative later. Is that me? Is that something here? All right, sorry about that. All right, so in any case, there's one other thing that we have to do in order to get this going, because the only equation we have, these are just values. The only equation we have only has volume and radius. It doesn't have a spot to utilize a rate of change of the volume or determine a rate of change of the radius. So we need to create a new equation that has rates of change in it. Starting from this volume equation, I'll write it as v of t. The volume at any point in time is 4/3 pi times the radius cubed at that same point in time. So you can see kind of similar structure to the cube formula, just messier coefficient. So if I want to know rates of change, I'm going to take derivatives with respect to time to get these sorts of the rates in cubic inches per minute and some other like how fast, like a time-related rate. So I'm just going to use prime notation. V prime of t would be the derivative of the left side with respect to time. So this would be then equivalent to our, this is where we're going to get to put in our negative 150. How fast the volume is changing at some point in time. I have to just have all the other corresponding pieces to substitute in and solve for what I need. But coefficient, and then taking the derivative of r of t to the third power with respect to t. Similar to last time, 3 r of t squared times, what's the derivative of r of t? Well, r prime of t, or dr dt. So again, this new relationship relates three quantities: the rate of change of the volume with respect to time, the rate of change of the radius with respect to time, which is what we're supposed to be finding. This one we know. And one other part here, the radius at the same point in time. Notice that we don't have the radius given. We have the volume given. So I'm supposed to be finding the rate of change when I know the volume is always the same rate of change, negative 150 cubic inches per minute. I need to know what the radius is somehow, and all I know is what the volume is. Any thoughts on how we can accomplish finding the right piece of information here? Hint? We have another relationship. We haven't used it for anything other than taking derivatives, but if you know the volume of a sphere, even though it's an unpleasant, weird numbers computation, you can find the radius, right? It involves dividing and a cube root. So if you know the radius, you can find the volume. If you know the volume, you can find the radius. That's what this relationship gives us. The other relationship helps us relate rates of change of those with respect to time, but this one, if I know that the volume is supposed to be 500, then the radius is something findable. I just have to, I don't have to make it look pretty, but I can divide by 4/3 pi and take a cube root. Because of weird situations like this that are just like, it's easy enough algebra, but messy numbers, if you want to estimate an answer, please, for next week's test, bring a calculator in case you need to do something like divide by pi, take a cube root, things like that. It doesn't have to be a fancy calculator of any sort. It can be any non-internet-based calculator. So it can be just a, like, as long as it has ability to do roots, maybe has a pi button. So any scientific calculator should be good. You don't have to have a graphing calculator. Just borrow a calculator from someone. Find one on Craigslist for $2 if you want. Whatever you want to do. It just needs to be able to do things like evaluate what this radius might be, which would be, well, in messy form, 500 over 4/3 pi, and then take the cube root, which I believe is approximately, I wrote this down earlier, let's see, 4.9. That's not something that I'm going to estimate by hand, but that radius, when the volume is 500, the radius is about 4.9, a little bit less than 5. So in terms of the given information here, if this last line, how fast is the radius changing when the balloon has a, if it said radius of 4.9 inches, that would make it more directly like the last problem we did. It had an easier sort of given information. But other than that, this question is pretty much like the last one. We have a volume formula. When we take the volume formula's derivative, we have to use a little bit of chain rule, and then we have some values to plug in. It's just this one we had to, well, use volume to find radius. So using volume to find radius sounds like a geometry question from high school. I'm sure you've done it before, but just with all the other stuff involved, don't let that sort of, like the simple math, slip your mind. Like, I had the volume, I need the radius. How on earth am I supposed to do that? Volume's related to radius. We have a formula. So don't fret. Just plug in approximately, or if you have a fancier calculator, you can use the previous answer feature. For the purposes of the test, so that you don't have to have a specific sort of calculator that keeps like 90 places of accuracy or allows you to insert previous answers without retyping them, answers to things like this would be rounded off, and it'll say like it's multiple choice. Choose the answer that's closest. So there'll be an obvious one that's closest and others that would only be close if you did the problem entirely wrong. So don't worry about like, I'm going to have to retype this because I only have a simple calculator. This class isn't really about computation, but at some of these problems we have to have a number to move onward. So we'll find this. But in any case, from here, you can see it's much like the last one, only, again, messier structure. I've got negative 150 equals 4/3 pi times 3 times 4.9, or however many decimal places of accuracy you kept, squared, times the thing that we're looking for. So again, to solve, we'd have to divide this time instead of this just being a formula solved for the item that we're looking for. So numerically speaking, multiply all these things together, do negative 150 divided by all of that, and it should come out here. Just if you want to finish this up on your own, try it out on a calculator to make sure you know how to calculate it properly. R prime of t should come out to be approximately, by doing that division there, negative 0.5. And the units on that, since it's how the radius is changing with respect to time, you can get by doing the same sort of units evaluation we did on the last one, but it should be inches per minute. Meaning the radius is shrinking by ½ an inch per minute at the point in time when the volume is 500 cubic inches, and all the while the volume is decreasing by 150 cubic inches per minute. At this particular point in time, this is how fast the radius is shrinking. It's changing by negative 0.5 inches per minute, or shrinking by 0.5 inches per minute, approximately. All right, so we had two geometry sorts of things, volume of a cube, volume of a sphere. Let's look at some trigonometry, because we did spend a little bit of time on trigonometry. It's good stuff to know. Helps with lots of other situations. All right, so let me just click this up really quickly. That's what we did. So here we've got a motorboat leaving a shore going in a circular arc at a speed of 28 kilometers per hour. The circular arc has a radius of 60 meters. Make this red. And I want to know how far the boat's distance from the shore is changing when the boat's traveled 150 meters around this circle. So this picture is maybe 150 meters. So like one radius length, 60 meters, would maybe be about here, 120 meters, about there. So there we're at 150. I would suggest don't try to put in all the numbers at once, but just thinking about in general, if you can imagine as the boat's traveling along this blue arc here, creating a variety of different angles, it's also making itself so that it's a variety of different distances from the shore. So if I want to know how fast the distance from the shore is changing, I'm not talking about along this arc. I'm talking about distance. Distance is a straight line, although we are on a globe, so however you want to consider that, but small circle. So I want to know how fast this is changing at the point in time when I'm over here. So if you can imagine, as if this red line, if I had GC out, if I could animate this red line going around the circle like that, the distance from the shore is that vertical part of, you can see like a triangle formed here, but the vertical part of that is changing. First it gets larger and then it gets smaller. At this point in time, if this is a fairly accurate representation of 150 meters, meaning 2.5 radius lengths or so, then I'm past the farthest point of the circle, or past the farthest point away from shore, and the boat is now approaching the shore. Now, the path it's taking is actually along the arc, but its distance from the shore is what I have as this dotted line here. So what we're trying to relate here is how fast is the boat's distance from shore changing? So how fast is this dotted line changing? As it travels around here, and it travels around this blue arc at a fixed speed, 28 kilometers per hour. Now, as a note, notice everything else is in meters, but 28 kilometers per hour would be how many meters per hour? 28,000, right? Yeah, 28 kilometers is the same as 28,000 meters. I'll just make that one change. So we have everything in terms of meters, meters per hour. Those rates ought to work better together. But again, I want to know how fast this length is changing relative to, well, where I am on the circle. I know how fast this blue line is changing. So I somehow want to relate the blue arc and the green dotted line there. And both of them are changing. When the blue one's getting longer, at this point, the green one's getting shorter. Earlier on, that wasn't the case. But they are kind of both related. You can relate one to the other a variety of ways, but they're both related to this angle here. How can I express this blue curve? Let me call it, let's see, A for arc length. How could I express the length of this blue curve in terms of theta? Well, this is our arc length here. However big theta is if I measure it in radians. Like if theta was 1 radian, then this would be 1 radius length. It would probably look like over here. So that would be 60 meters. If theta was 2 radians, then the arc would be 2 radius lengths, or 2 times 60. If theta is just some number of radians, then this blue length is going to be, well, however many radians that is, times the length of the radius. All right, so it's theta radius lengths, or theta times 60. So 60 theta, theta times 60. But the length of this blue part here is related to the angle. Now, the green part, how is the length of this green part? Let me call this y since it's a vertical line. How is the length y related to angle theta? Well, what trig function is involved in this relationship between that angle and that vertical distance above the horizontal here? Yeah, that's a sine function. So there's a sine function that relates them. So the hypotenuse of this triangle, if you are thinking like triangle trig here, is 60, right? That's the radius of the circle. Sine values are always between -1 and +1. This is going to be something positive as a length here, but it's not going to be between 0 and 1, right? It's a fraction of 60 between 0 and all of 60, right? So it's going to be that fraction given by the sine function, again, multiplied by 60. I'm going to put the 60 in front so it doesn't look like it's theta times 60 like the last one. But, I mean, if you're thinking of, like, the sine function, if you're thinking sine is opposite over hypotenuse, you could think sine is y over 60, something like that, but just rearranged to the quantity that we are looking for the rate of change of with respect to time. It's related to this guy here, but this one's tricky because we've got two things that are kind of related. I know the rate of change of A, that blue curve with respect to time. It's 28,000 meters per hour. This number here, this is the rate of change of A, that blue arc, with respect to time. Now, it's only valid for a little bit because then the boat runs into the shore. So small domain of time here. But this is a specific value of a rate of change of this arc length. This arc length is increasing by 28,000 meters per hour. Now, it's not going to go for many, many hours. It's just going to be for a small amount of time. But that's the rate at which this expands from 0 to, well, half a circle worth. So what I want to find, how fast is the boat's distance from shore changing? That's dy dt. So somehow I want to have y and a linked together in an equation. Yeah? Nope. Nope. We don't have, yeah. So theta is that obtuse angle there. So if you're thinking about that triangle there, the angle inside the triangle is 180 minus theta if you're in degrees, but we're not actually concerned about that triangle. We're concerned about the y value. So yeah, so we just need, yeah, this length here is the sine value of this obtuse angle. It's the sine value of any angle in circle terms is defined by the distance that the terminal side of the angle is above the horizontal of the circle that we're considering. So imagine your axes as the shoreline and a vertical line here. Ooh. I don't know why it did that to me. Sorry. All right. So just trig definitions. Yeah, I was drawing just fine. Hi, sorry, this is being touchy today. Maybe. All right, so our trig definitions for any angle of any size. If you look at the terminal side of the ray of the angle in standard position, its distance above the horizontal axis is considered to be the sine value in a unit circle, or r times that sine value in a circle of radius r. The distance left to right that this is the cosine value. So in a unit circle, or r times the cosine value in a circle of radius r. So it just doesn't matter what quadrant we're in, it's the same for any sort of angle. So sine is that vertical distance, either above or below the horizontal, and cosine is the horizontal distance, either left or right of the vertical axis. And again, like if you're talking about one unit circle, it's just that that measurement itself is the sine or cosine value. If you're talking about a circle of radius r, just scale that trig function up by a factor of r. So let me get this to function again. All right. Are we going to write, or are we going to try to do something else? All right, so the thing is that I need to figure out how dA dt and dy dt are related. So I need a and y in the same equation instead of having them as two separate equations both related to theta. But this is maybe sort of similar to some things that you did in optimization questions where we had like a main overall function and then a constraint that when we used it, it helped break our function down into something that's just a function of one variable. So using somewhat substitution. We're thinking of this as a system of equations. I can eliminate theta from this. I can write y as a function of a, or a as a function of y. Now, I can say by substituting, like I could substitute in a, some formula of a in place of this theta, or I could substitute in some formula with y in place of this theta. But I don't want to get into inverse signs, so I'll do it this way. Instead of y equals 60 sine of theta, well, if a is 60 theta, then theta is a over 60. So instead of writing sine of theta, I can write sine of a over 60, or 1/60th a if you prefer. But now, after a bit of work, as you can see, this is not an easy problem. Don't let my, I'm saying it quickly, don't let that make you think that this is super simple. This is not simple. This is really complex. We had to involve two different varieties of trig, like talking about arc lengths and talking about measurements, vertical and horizontal, and then create a single equation out of those that relates distance from the shore and distance along an arc. Because what we're trying to relate is how fast is the distance from the shore changing relative to, well, knowing the fact that how far I am around the arc and how fast I'm going around the arc. So with this equation, the starred one here, if y is 60 times the sine value of a over 60, then I can find the rate of change of y with respect to time, which is what I'm actually looking for, by taking a derivative of this with respect to time. So dy dt, taking a derivative of this with respect to time, I'm going to think of this a as a of t. So if I have sine of a of t over 60, and again, if you don't like a function over 60, I can think of this as 1/60th a, or 1/60th a of t. But to take the derivative of this side, that's a coefficient of 60. Derivative of a sine function is a cosine function of the same thing. But then chain rule, times the derivative of a over 60, or times the derivative of 1/60th a. Well, it's got a coefficient. And the derivative of a, linear a, function is a prime of t, or dA dt. So this here is the derivative of a over 60, or 1/60th a, where I'm considering a to be a function of time. So a is a whole formula. Its derivative is a prime of t, or dA dt. I just had that multiplied by a coefficient of 1/60th. And there's some cleaning up, simplifying we could do here. And I'm just going to rewrite this quickly. But the rate of change of the boat's distance from the shore with respect to time would then be cosine of a over 60 where A, again, is this arc length here. We have a value for that at the time we're interested in, times d/dt, the rate of change along the arc, which we have a value for that also. So we're trying to find dy/dt. All we need to know is a value for A, this arc length here, which is 150 meters. And the speed at which we're going along the arc, dA/dt, that's our 28,000 meters per hour, to have the units properly here. So I do cosine of 150 over 60 times 28,000, and that will tell me in meters per hour how fast the boat is approaching the shore. Notice if you do this computation, you will get a negative value for dy/dt, which means that y is shrinking, which should make sense. The reason that negative comes in is because we're doing cosine of 2.5. Cosine of 2.5 is going to come out something negative. Cosine is that, in terms of this triangle, it's the horizontal bit, but it's in the left side here, so it'd be physically a negative result. It's the x-coordinate of this point. So in any case, I believe this comes out to about negative 22,000. dy/dt is approximately negative 22,000. And the units on that would be, again, our meters per hour. We change this kilometers per hour into meters per hour. If you want to put it back, you can say, oh, it's about negative 22 kilometers per hour, meaning that the boat's approaching shore directly, straight line speed of 22 kilometers per hour. It's traveling at a speed of 28 kilometers per hour, but its distance to the shore is decreasing by 22 kilometers per hour, or 22,000 meters per hour. Or if you wanted to talk about smaller time units, because I'm sure this whole trip would only take, not very long, you could change the whole problem into something like minutes or seconds instead. But rather than doing unit conversions, I'll leave it at that. So 2 other quick things today. We've got 5 minutes left. I want to introduce one more problem and also tell you what we're going to be doing the remaining few days of class. So the one more problem that I want to show you, and just kind of a thought on this, is about a street light. So we've got a street light, somebody walking away from a street light, and talking about their shadow and how fast their shadow is moving along the ground, the tip of their shadow. So street light's at the top of a 16-foot tall pole, and there's no picture to go with this one, unlike the speedboat one, but maybe we can imagine this. We've got a street light. I'm going to draw, with my high-tech art skills, street light and a person. And the person is, at some point in time, 35 feet away from the base of the pole. Here, now it looks like a person, or a key or something. There, now it's a person. So at some point in time, this person is 35 feet away from the base of the pole. And just in terms of shadows, if you don't remember doing problems with shadows and angles and stuff from a geometry class, the light goes at all these different angles, but one of them will hit the top of her head, and the top of her head will be projected onto the ground. The end of the shadow would be out there someplace. So that we end up with this sort of, imagine those are straight lines, a triangle situation. We've got a triangle inside a triangle, where overall I've got a triangle that is a 16-foot tall pole here that goes out who knows how far this direction, a 6-foot tall person here, and shadow there. We've got similar triangles, one with 16 and one with 6, and I don't know what this whole length is, 35 plus something. Here, I'll write it as that way. And this is just the something. But in any case, we've got some relationships here between these. I'll want you to think about this before next class. We will go through this at the beginning of next class. But what we're going to do the rest of next class, this is the last related rates example that we're going to go through. What we are going to do next class, remember tonight you've got your optimization homework that's due in iMath AS. I am going to assign to you a quiz tonight, a Canvas quiz, but it's not going to be a standard, actual quiz. What it'll be is a poll where I'm going to ask you of the questions in the optimization homework, which one you'd most like to go over in class on Wednesday. And I'll pick a couple of those, the couple most frequently asked for optimization questions we'll go over in class on Wednesday, as well as go over this. And that will be the end of the material that's going to be on your exam 3 next week. Your exam 3 next week, we will have a Monday meeting before that. We can wrap up any last details, but Monday and Friday of next week, we'll be talking more about kind of wrap up fundamental theorem of calculus, put it all together, make sure we know some other fancy things we can do related to the last couple of iMathAS assignments, which once you get started, they're not particularly hard, but I do want to discuss that a little bit more, but that'll be next week. All right, that's it for today, and we're almost done with the semester, amazingly enough.